Alright, hi everybody. We are going to take a look at some classic Newton's laws style problems in this video. So I want to review some of those with you. First of all of these problems you're going to tackle with the same exact strategy. There's really a four-step process you want to take a look at here. The first step in this strategy is always draw a picture. Really, you want to draw a free body diagram. We worked on those in class. You got a chance to see those on the website. And that thing, once you get the free body diagram done and right, you're well on your way to finishing the problem. Once you get that, you've got all of your forces kind of sorted out. So the second thing you want to do is take a look at Newton's second law. F net equals ma, where you think about the direction of forces and the acceleration. So I would say also in each direction, any direction you're interested in. Sometimes you do it in the x, sometimes you do it in the y, whatever. It works for all the directions. So we just want to be very sure that we're looking in the right directions at the right time. And really the third step is everybody's favorite, algebra. Because once you get the equation, it comes down to just trying to solve for whatever the thing is that's unknown. Maybe it's a force, maybe it's an acceleration, and then there is sometimes it's kind of optional. I'll start. The fourth step is usually once you've unlocked this problem and maybe you have a force or an acceleration that you didn't have before, then you might find that you have to solve a kinematics problem. That was kinematics, remember, was modeling motion without knowing why it's happening. We just kind of said, okay, we got some motion, we have an acceleration. Now you know why the acceleration's happening. So, okay, what are some different kinds of problems we can look at here? Well, we're going to take a look at a few. We'll see how far I can get with this. We're going to take a look first at a box on a horizontal plane, like the one you see here. So here is this box, and let's say it is being tugged to the right with some sort of applied force. I'll call it F-ap. Now, what else is going on? You notice just in sketching out and thinking about this problem, I'm already drawing a free body diagram. Well, if it is, let's say, accelerating to the right here, you might think, oh, I just need to worry about that. Well, there's other forces that could be at play here. In fact, we know that this box has weight, so I could draw F sub g down here, and I know that the ground is going to be pushing up on it, so I could draw what we call the normal force up here. If this has friction, which this problem doesn't deal with friction yet, we can imagine there's a frictional force going out this way, but in this case this is what we have. And so check, I've done step one, check free body diagram, did it. Now I got to think about Newton's second law, F net equals ma, and think about what I want to do with these forces here. Well, let's say we're interested in finding what this acceleration is. So maybe this is a number. I'm just going to solve it symbolically here, but let's just say it's a number. Well, you know, up and down, there is no acceleration. There's no acceleration in what we usually think of as the y direction, the up and down. This force, the normal force, is perfectly canceling out the gravity force, so F net equals 0. So there is no acceleration, but there is to the right here. So the y direction doesn't really get us that much. All it's going to tell you is that if you do F net equals ma, you're just going to find that the normal force equals a gravity force. But if I look in the x direction, if I think of the x as being to the right, I'll see, okay, F net in the x equals ma in the x, and that's going to mean, well, my only force acting in the positive or negative x is just this F-ap force, and that's going to equal the mass times the acceleration in the x direction. So guess what? It's pretty straightforward. In this case, the acceleration is going to be the force F-ap over the mass of this particular box. And so we looked at a lot of different ways we can do this. It doesn't have to be one particular force, you know. You could have a box here with several forces on it. Maybe there's a force this way, and then there's sort of a force tugging back, or maybe there's two forces tugging back. So you gotta have to play the F net tug-of-war thing with this and just ask yourself, okay, what is the net force if there's three of these forces all interacting? I've got to get the net force acting on this thing in order to find the acceleration. You also might have a situation, I think we're going to look at one in class, where you might have a force acting at an angle. So imagine a force where you're pulling up like that. So what does that mean? Well, remember, that means that you're tugging to the right, and you're tugging up at the same time. If this thing has no acceleration up and down, if the acceleration is only to the right in this case, I would need to know this angle, and I could say, okay, the only force contributing to this thing moving with this acceleration is F cosine of theta. That is my F net, so that will be equal to ma. So there's a couple different variations on this, but that's one classic one. The next one that we're going to take a look at is, let's look at moving vertically. What's that about? Well, let's imagine we have a ball maybe falling. So if we have, let's say it's a ball on a string. We could, if it was just falling, we could say, okay, he's got the gravity force pulling him down, and that's it. I could say that equals ma, solve for a, and it turns out it's little g. But let's say this thing is actually got a string attached to it, kind of yo-yo style. I could talk about the tension in this string, and if a equals 0, well then this force perfectly cancels out this force. And so if I'm not accelerating t, if a equals 0, t is going to equal the gravity force. That's just what happens, because they cancel each other out. But maybe we have a situation where this yo-yo like object is not balanced. So it's got some weight, but it also has a big, let's say, tension force lifting this thing up. What do you do now? Well, let's say to ourselves, okay, if the acceleration is up, that's what I care about. I'm going to call up the positive direction. And if I look in that direction and say F net equals ma, what am I going to get? Well, if up is positive, I'll have t, this force, minus the gravity force. They're sort of in a tug-of-war thing here, right? And that's going to equal ma. So now my acceleration or let's say maybe we know the acceleration. Maybe we don't know what the tension is. Maybe we have a certain desired acceleration and want to find out what tension is going to be in this string in order to get a certain acceleration. Well, I could say that that tension force is going to be equal to the weight of this thing plus this term here, ma. So you can see that tension is going to be way more than just the weight. It's going to be the weight plus some amount, the amount that it's going to take to accelerate this thing. And that's when that little demo we saw in class, when you pull on the thread to really try to accelerate a mass, it might break the thread because maybe the thread can't handle that kind of a tension. It can handle enough tension to hold the weight, but not enough to make it really accelerate. So this, if you've ever gone grocery shopping and you rip the handles on the bags, things like that, that kind of stuff happens all the time. If you think about maybe the example of maybe a helicopter. So if you have a certain a helicopter, maybe we might look at one of these in class. So here's a little helicopter here, and he's just sitting there. That they can generate on themselves a certain force to lift them, right? The air basically is lifting this thing, and it's got a certain weight down. Well, if you add cargo, you're going to have more weight down. So this lift force, F lift, better be enough to not only be equal to all of this weight, but actually be equal to it and then some, right? To give it an additional boost so it can actually accelerate upwards. So that's moving vertically. I'm going to break it up. We're going to take a look at a couple other examples here in just a minute.